Right. Today we will learn about the log and synchronization, and then we will learn about more detailed implementation about how we can implement the log primitives, and then how we can create critical sections using that. And then for lab 3, I ran the grading script last week, but I will run the grading script again today. So maybe tomorrow you will see that the submitted a graded score for lab 3. And then if there's any kind of error, please feel free to let me know. And then the grading script will run again on this weekend too. And then the lab 4 has been started. So the part A is easy, but the part B is quite difficult. So please start the lab 4 as soon as possible. And then try to finish up to the 65 points mark. So finishing part B will let you get in there. Yeah. And then the part C is actually not that hard. So please put a lot of time on part B, and then once you finish it, don't give up at there, and then try to finish part C. So the part C is not that difficult. And then we will have another quiz. So I have to have have 3 quizzes in the 10-week schedule. So that's why we are having another quiz in the coming weeks. But the quiz will follow the same policy. So open material, 3 attempts, and then I will take the best score. So you can use that time for recap and studying the materials that we learned for the recent few weeks. And then for quiz 2, we covered most of the virtualization part. So in quiz 3, we will cover the user corner switch system call, and also for the preemptive multitasking and the copy and write fork. And then we will mainly focusing on the multi-threading and synchronization, threading, concurrency bugs, those kind of stuff. And then most of the quiz 3 part will be learning by today and the lecture on Thursday. And then we have a sample quiz, so you can download the sample quiz from the prior offering of the course website. And then the one question from Zoom was when did he say lab 3 would be graded? So the lab 3, I will grade it today again. So you will see the submitted lab 3 score tomorrow. And then I will also run that again on the weekend. All right. So these are a little bit of logistics, and then let me move on to the contents. So from the last lecture, the lecture before we are taking the quiz, we learned about the difference between the process and thread. So to utilize process as a multi-threading, multi-processing primitive, what we can do is we can create another process to run the same program using a fork system call. And basically what we are doing is we are running one program, and then in the middle of the running one program, we would like to clone the exact same instance and then do something else. So the fork system call, basically, they will clone every single memory space. And then what it does is it will create the new virtual memory space by doing the deep copy of the page directory table and also each of the physical pages. So the fork system call, what it does is we need to copy the entire memory space. And that's why the counter variables in the parent and child, they do not share anything. So that they do have to separate the physical memory backing each of this variable. So in this kind of the code snippet, what we are doing is after having a fork, we will run both parent and client, parent and child. We run the countof function. So they're counting up the global variable one by one till 1 million. And then because in the process scheme, we do not share anything. So the counter here is stored in a different physical memory than the counter of the child. So what we will get is each will count up until 1 million. There's no share at all. So the problem is that we can easily run the multiple instances of the same program, but the problem is we cannot share the data. But in some cases, if we want to speed up the execution of the certain work, we would like to spread a lot of CPU cores working on it. But in the meantime, we would like to share the data. So in such a case, we must use we can use another primitive called thread. And then the different thing that in thread is that, so instead of using fork, we will use pthread create. And then what thread creation will do is it will not copy anything. It will use the same CR3 value. So it will reuse page directory and page table. So that's why I marked all the memory layout as a dotted line. So it's existing there, but they're not physically existing. So all the kernel, others, user experience stack, or heap, program, global counter, all these are referring to the physical memory backed memory at here. So that they will use a parent thread and then child thread will share all of the thing except for the user stack. So that whenever we create the new thread, we need to create the separate execution environment. So the separate the stack to store the local variable or the call stack, those kind of information, so that we are actually creating the new stack to a child thread and then run it. And then it is not depicted well in here because the parent thread and then child thread will share the CR3 value so that it will completely share the entire virtual memory space. So I depicted it like a child thread will have a user stack 2 here, but that is also visible from the parent thread too, because they are actually sharing the entire memory space. So what thread creation does is just creating the new stack and then run a new thread on it. So you can think it as it is a process, but we did not create any kind of page directory, page table, then just assign a new stack. And because we are doing like this, all the others are shared. So in this kind of the code, after creating a thread, so the main thread will run count up, and then child thread will run this function count up. So they're both child and parent will increase the counter value because these memories are fully shared. So the result is something like this. So we are expecting that to have a result something like a 2 million because parent count up until up to 1 million, child count up 0 to 1 million. But the problem is that what we are getting as a result is not 2 million at all. And then every time we run this program again and again, we will have an inconsistent result. Yeah. So the reason why we cannot get the 2 million was the so-called data racing problem. So even if the counting up, the code for the counting up the value, so it looks like one line, but in assembly language, that could be split into 4 lines. So the first line is for the fetching the value 1, and then the second line is for fetching the counter, and then third line is adding the value, and then fourth line is writing the value. So the problem is that, so we can load the value, load the counter, and then add the value. But before storing this newly computed value to the counter value, if the another thread started to run and then load this value. So even if thread 1 has started first and then tried to update a counter, that value has not stored at here this time, then the thread 2 can fetch the old value. So if any of the execution, any of the load execution can happen between the load and store of the one execution, then that could ruin the consistency of the calculation result. So this value is not being forwarded to this calculation. So the both of thread will count 1, even if each of them try to count 1 and 1. So we would like to make that kind of a calculation to be like a counter value 2, not 1, to be consistent. So to do that, we conceptually learned about the mutex, mutual exclusion, to create the so-called critical section that prohibits any kind of the concurrent execution happens for a certain part of the program. So conceptually, we can create the critical section using lock and unlock. So we will learn more about how we can implement the lock and unlock in detail. But at this time, just think it as a lock will prohibit any other thread get into the critical section. And then only after unlock has been called, other thread can get in. So with this kind of the lock primitive, so we can guarantee that the only one thread will be in a critical section. And then after one thread get into the critical section, we run 4 instructions for counting up the value. But suppose the other thread 2, would like to get into that critical section, but because the lock was acquired by the thread 1 has not been finished yet, they need to wait in the lock function. And then after thread 1 finishes updating the counter value and then calling the unlock, then this call of the unlock will signal the other thread to proceed. So this thread 2 can run the count up, but while they are executing in here, if the another thread try to get into the critical section, that is also blocked. Yeah. So after the preceding thread finishes execution and then call unlock, then another thread can continue the execution. Yeah. So that's the basic concept of the mutex. And then by doing so, we will see that all the load store of the counter value will be finished before the next loading of the value. So that's why we can make the result consistent. So there will be no intervention between this load and store from the other thread by creating the critical section. Yeah. And then I believe like most of you guys are curious about like then how we can create that kind of the lock and unlock primitive. So if we have that kind of the door, then we can easily create this kind of critical section and then use that for the synchronization. And then for the most of time, you have done like that because like there's a library called the pthread, and then pthread support mutex. And then in some other languages, if you have used for the synchronizing multi-thread, you might have used the mutex in Python, Java, or some other language. But all those implementation cannot be possible if the CPU does not support this kind of the lock primitive. And then we will learn about like how we can implement that in detail. So to create this kind of the critical section, so if we can implement the critical section, we can easily synchronize all the thread and then remove all the data erasing issue. And then the question is like, how can we create this lock and unlock, and then allow only one thread can enter the critical section each time? So for example, suppose that right now thread 1 is running, and then thread 2 and 3 are waiting. And then suppose this thread 1 is finishing with the unlock. Then what we need to do is like we need to signal only one thread, either thread 2 or thread 3, to let them get into the critical section, not for both. So think about it. If we set a lock variable as 1 as acquired, 0 as empty, then so when we are running thread 1, lock value will be 1. And then thread 2 and 3 will wait because they are observing lock value as 1. But we can implement unlock as a setting the lock value as 0. Then once the thread 1 sets the lock value as 0, both thread 2 and thread 3, they can observe. Maybe the thread 2 can observe that value, lock value 0, ahead of time than thread 3, then they will get in. Otherwise, thread 3 will get in, but there's a case that the both the thread 2 and 3, at the same time, they observe the lock value as a 0. And there is a case that both of them get into the critical section, so that we need to be very careful for designing this kind of the primitive. Yeah. So let's take a look at how we can implement the lock, and then let me start with the very naive implementation. Yeah. So what we have observed from the lock conceptual behavior of the lock and unlock function is that, so once one of the thread get into the critical section, the other thread need to wait. So computers are dumb. So like you cannot say like for the computers and then do nothing for a while. Yeah. So what you actually need to do is like if you want to do nothing with the CPU, then you need to either halt the CPU. So in left 4, you will see that if you have a remaining CPU cores and then there's no jobs to be scheduled, then like you will run the halt instruction in CPU. Then that actually stop the CPU. But for the operating systems, we can do that because even if so the halt instruction actually stop the CPU, and then that will be woken up again whenever there's a timer interrupt comes in. So for the operating system side, we can completely stop the CPU. Then we can wait for the CPU get up later with the interrupt. But lock and unlock, these are not the operating system primitives. So that we should also use that in the user level programs so that we cannot do that and then run halt. So that instead of the running halt, we spin for waiting. So that's actually we are actually running a while loop. So let's think about how one thread can get into one of the critical section while the blocking all the others cannot enter the same critical section. And then in implementing that kind of log and lock, we will use a semantic that. So the lock will be a variable in the memory. So that we will have it as a log as a integer pointer. And then if that value is 1, then we will regard that like the one of the thread is running inside the critical section. And then if that value is 0, then we will regard that the no thread is running on the critical section. So anyone can enter the critical section. Then take a look at this bad lock implementation. Yeah. So what we can do is, so if the lock value is 1, then we will stay in the while loop. So by doing so, then suppose one of the thread is running on the critical section, then we can regard that the lock value is 1. Then thread 2 and thread 3 will observe lock value as 1 and then keep looping inside there. And then what this unlock function do is this unlock, what it will do is like it will just set the lock variable value as a 0. Then once this thread 1 calls unlock, which is setting the lock value as a 0, then the other threads, thread 2 and thread 3, they are waiting on this while loop, and then they will observe lock value became 0. Then what will happen? So it will break from this while loop, and then immediately after that, it will set the lock value as 1. So it's something like, if the lock variable value is 0, then you can regard that as a door is open. And then once you get into that door, waiting until lock value becomes 0, then you will set the lock variable as 1. That's actually closing the door. So that once you get in, you will close the door. And then after you finish all the execution, you will open the door again. And then all the other thread will be waiting in this while loop. And then once they observe the lock variable become 0, then they will break from this while loop and then try to enter the critical section. But this implementation is not great because it will result in the inconsistent result. So that's why I named it as a bad log. But please refer this as like the conceptual, and then we will gradually building the log and log primitives. So based on the observation that the only one thread can enter, and then if we can simply use a 1, 0 log variable, then you can regard this as we can do it something like this. But let's take a look at why this implementation cannot safely synchronize a thread with the examples. So this is the spin log, and then what we will do is at the log, we will run while loop and then wait until log variable becomes 0. And then once we observe that, we will lock the door by setting the lock variable as 1, and then we will continue to execute in our critical section. And then after that, we will open the door by setting the lock variable as 0. Then suppose we have a thread 2, and then after this thread got in, and then set it as a lock value as 1, then this thread will observe lock value as 1, so it will stay in the while loop again and again. And then suppose another thread 3 comes in, then because this thread 1 set the lock value as 1, then it will wait in the while loop. And then once this thread sets the lock value as 0, then this while loop will be broken, and then the second thread can set it as a lock value as 1, then they can run it. And then while this thread is running, the thread 3 should wait until while loop again and again. Yeah. So this is the how spin locks should work. But the problem is that this while loop and then setting up the lock, these are not atomic. What that means is that there could be a case that when lock value becomes 0, and then before the first thread sets a lock value as 1, there could be a chance that this and that thread can break out of the loop and then get into the same critical section. And then you can actually run all these implementations because from now on, I will introduce several spin log implementations, and then you can check about those implementation in this repository. So if you are on the OS2 server, you can clone that repository and then build it, and you can run it to see the actual result. And then you can also take a look at the code. And then it includes 5 different log implementations, including bad logs. So you can take a look at how the bad log or other logs are implemented in code. And also you can take a look at how it is actually implemented in assembly, in detail. And then for these kind of the log examples, what it internally does is, so that in the lecture example, I just put the 2 thread, the thread 0 and thread 1, and then try to count it up to 1 million. So it was not 2 million. So that case is too simple. So what I created about the program is that in the main, there is a count variable. So there is a count variable shared across the entire thread. And then the main thread will fork 30 different threads. And then each of the thread will count up this counter value for 10,000 times. So it's something like this. So each thread will count up for 10,000 times. And then we have 30 threads. So a consistent result, if it is synchronized as well without data race, then we should observe 300,000 as the result. So inside of the log.c, so what I did is they will create the 30 threads, and then each of the thread will count 0 to 10,000. So correct result must be 300,000. So, and then internally, I use a pthread create to run the thread function. And then thread function is just counting up 10,000 times. And then I will create the 30 thread. And then join here means that I will wait until all the thread finishes. So after all the thread execution gets finishes, then I will fetch the counter value and then print it on the console. Then internally, it will count one by one, but to create a lot of the context switch, I intentionally insert the sched yield. So that what it will do is like it will have a 30 thread, and then it will just count up, and then asking for the context switch, and then do it again and again to create some of the complex the scenario about the 30 threads are competing each other to get into the critical section. So the sample result would be this one. So like correct result need to be 300,000, but with the no lock, so if I didn't use any kind of lock, then the count value is like a 36,000. It's far less than the actual value. And then every time I run it, this value will be changing because like it is not synchronized. So like it will result in the inconsistent result. And then another thing that you can practice is that, so this is a disassembly of this count no lock. So the count up without any kind of lock. And then we can definitely see that the loading of the counter, add the value, and then like the storing of the counter. So these are split into the 4 different instructions so that there's a chance that we can get in and then interfere for the race condition. And then we have several log examples. So this example is like with no lock, and then with the bad lock that we use a while and then log setting variables. And then we will also see the rest of the log implementations with the different options. So let's start with the first lock candidate, bad lock. So let's take a look at this point. So we will have a lock and unlock for creating a critical section. And then in bad lock, what we will do is, so we will use the semantic that if the value of the lock is 1, then that's acquired. We cannot get in. If that is 0, then we can get in. So at the lock, what we will do is like we will wait until lock variable becomes 0. So if it is 1, stay in the while loop. And then if it gets 0, then break it and then set it as a 1. So close the door to not making any other thread can get in. Yeah. And then bad unlock. So it will just set lock variable as 0 so that some other thread will observe the value 0. So break this while loop and then get into the critical section. And then after creating these 2 bad lock and bad unlock, so that we can create the critical section using the log and unlock and then just count up. But this implementation has a problem because my computer is stopped. Because these 2 parts. So the first part is like a checking of if the lock variable is 1, and then setting of the lock variable as 1. These are 2 different parts. So that we are actually creating the critical section from here to there, but the problem is that this lock part is parted as 2. So that means, so if thread 1 so suppose thread 1, 2, and 3 are there. So the 1 was the running thread, and then that thread will run bad unlock to make it as a lock variable 0. But suppose the case that the thread 2 and 3 both observed the lock variable as 0 and the while loop. Then they can break at the same time. And then later, thread 2 can update the lock variable as 1. And then thread 3 can update the lock variable as 1, so that there is a case that the 2 or more thread can get into the critical section. So if I run the critical section implementation using like a bad lock with the 30 thread, then I will get the result of the counting value as a 48,000, and then it'll keep changing, so inconsistent. And the reason is like that there is a race condition. And then to check the race condition, we cannot determine that in the source code. We need to take a look at the assembly lines. So this is the bad log implementation in the source code. And then this is the bad log implementation of the assembly line. So what we are doing is that, so this is a lock variable, and then we load lock variable into EAX, and then compare that if it is 1. And then if that is 1, then we will loop on it. So that these 3 lines are actually the while loop. Yeah. And then there is another instruction storing 1 to the lock variable. So we can regard these 3 instructions are for the while line, and then the last instruction, the 4th one, as the second line. Yeah. So there is a chance for like having a race condition, and then think about the case that this is the thread 2, and then this is the thread 3. And then suppose thread 1 release the lock by setting the lock variable as 0. Then thread 2 will first observe 0, then break from the while loop. But before updating the lock variable, thread 3 observes unupdated lock variable, so that's a 0, so that they can break it here. But at the time of the breaking the while loop, the thread 2 updated value. So this update is not visible when another thread checks about the lock variable. So there is a race condition. So the store of the variable must be finished before the next load of the variable, right? So the same thing happens. So because of this kind of the race condition, yeah, there is a case that the both thread will observe the lock variable 0, then the 2 or more thread can get into the critical section. Yeah. Any questions about this implementation? So the important thing is like we load the value and then store the value. So lock variable as a 0, observe 0, and then store 1. And then these 2 are apart. So that's why there's a race condition is happening. So we know that this implementation, while loop to guard the lock and then setting the lock variable 0 to open the door, is bad, because after running the thing, we will get the inconsistent result. And the reason is we have multiple instructions for loading of the lock variable and then storing of the lock variable. So the same thing happens. So the original problem of the race condition was for the counting up the counter value was even if we have a 1 line of the code for counting up the code, counting up the value, then that could be split into 4 instructions, and load and store are apart. So some other thread can involve in the middle, and then same thing happens here. So the important thing here is that we need to make the load and store as a single instruction to make that not any kind of the thread or not any kind of the instructions can intervene the execution. So the CPU designers create the mechanism for that, and we call that as a test and set. And then we call it as an atomic test and set operation, because in the CPU instructions, we cannot split it into multiple instructions. So we will do test, actually the loading of the value, and set, storing of the value in a single instruction. So the problem was like a load and store were apart. So that's where the race condition can come in. So to remove that, we need a way to test if lock value is previous lock value is 0, then we would like to set the lock value as 1. Yeah, we want to do that. And then we want to do that as a single instruction. Yeah. Not like these 4 instructions. So yeah, because like any other thread can get into there. So how can you do that is like in x86 CPU, there is a hardware instruction called the exchange. Yeah. And then that serves as an atomic test and set operation. And then actually we are doing test later. And then exchange is actually the swapping the 2 values. Yeah. And then how we can use that is, so suppose this is an exchange, EAX and RDI. So you can regard RDI as a lock variable because this is a memory operation, and then EAX as a value 1. So this exchange operation, what it does is like it will exchange value 1 with the value stored into the lock. Yeah. So it will swap the value with the single instruction, and then later we will test EAX value. So that actually stores a previous lock variable value. So if that is 0, then the current thread acquired a lock. If that is 1, then it means like previously the lock variable value was 1, so that they cannot get in. Yeah. So this is how we can make a load and store instruction as a 1, and then like make the lock consistent for the synchronization. And then let me explain a little more detail about the exchange instruction itself. So the exchange instruction, what it does is like that it will swap the data in memory and then value in the register. Yeah. And then what we would like to do is, so that we will always set the lock variable as 1. Because no matter, so log was acquired, value was 1, we will set it as 1. If that was 0, we will always set it as 1. But the different thing is that after rerunning like this kind of thing, for example, so what we will do is like moving 1 to EAX and then exchange lock variable value and EAX. So if the previous lock variable was 1, then we will write 1 to the lock variable, so the lock variable will be 1. But the interesting thing here is that we will get the EAX value as a return value of this instruction as 1. So that if the EAX value, the return value is 1, then means that previously the lock variable value was 1. So has already been acquired. So in this case, so if the previous lock variable value was 1, we will get the result as 1, indicating that some other thread is running, but we can keep the lock variable to be 1 so that no one else can get in. But suppose the lock was not acquired and then open to anybody, then if that instruction runs, then it will set the EAX value 1 to the lock variable. So it will close the door, but the EAX value will fetch the previous lock variable. Yeah. So with the single swap, we can combine load and store as a single instruction, and then we can check later. So the checking of the thing that does not affect on the synchronization. So the important thing is about the data race is that we need to combine load and store as a one single instruction. Yeah. So the rest of the things are like they explaining about this instruction itself. So what this instruction can guarantee is that, so this is a single instruction, and then if the first thread runs it, then there is no way that some other CPUs running the same instructions at the same time, actually that's actually the organized by the memory bus. So when CPU issues an exchange instruction, it will actually physically, electronically lock the memory bus. So even if you have like the quad core or octa core, multiple cores in your laptop, so once one of the CPU core issues an exchange 1 with the lock variable, that kind of command, then all the other CPU cannot access memory. Only after that instruction has been retired, some other instruction can run for loading the memory. So the exchange instruction actually guarantees that if I'm running this instruction, there is no other CPU runs the same the loading the memory at all. So that it is guaranteed that you are the only one will execute this instruction. So suppose the case that the lock variable was 0. Then suppose you have a 30 thread, and then for the exchange instruction, it is guaranteed that the only one thread can execute that exchange instruction. And then after running the exchange instruction, lock variable will become 1 immediately. Then all the subsequent exchange call will return the lock variable value as 1, because the first one will set the lock variable as 1. Yeah. So this is the disassembly of the exchange-based lock. And then let's take a look at how it goes. So it will move 1 to EDX, and then put that to EDAX. So it's something like we will put the 1 to EAX, and then RDI stores the lock variable address, and then we will exchange 1 and the lock variable value. And then if that value is not equal, is actually equal to not 0. So if that value is not 0, that means like a previous lock value as 1, then it will loop again and again. And then only if they observe the EAX value as a 0, then it will break out of the loop. Yeah. That's how it works. So this is where exchange happens. So with the single instruction, and then CPU lock the memory bus, and then it is guaranteed that no other CPUs are running at the same time. And then later, they can determine like based on the previous lock variable stored in the EAX value, they can determine is a log acquired or not. So once you understand the semantic of the exchange, then like it'll be it's understanding about the rest of the things are very easy. So the important thing is that after running exchange, we will swap the EAX value and the variable in the memory. And then after running exchange, if the EAX value is 0, then that means that we acquire the log. And then we can safely assume that the log is closed, because in exchanging the variable, we will always write 1 to the log variable. And then if the EAX value is 1, that means the previous value of the log variable was 1, so that you didn't acquire the log. So we need to wait in the while loop again and again. Yeah. So so we can implement the exchange lock using exchange primitive in the code. So that this exchange primitive, what it will do is like it will swap this value 1 and then value stored in the lock variable. And then this while loop, if the return value of this exchange call is 1, that means previous lock variable value is 1. So we need to keep wait in the while loop. But if that becomes 0, we can break out of the while loop and then run the critical section. And then unlock is just storing 0 to there. Then all the other thread running exchange, only one thread will observe that value becomes 0. Then they can break out of the while loop and then run it, and then do it again and again. Yeah. So this is the critical section. And then the CPU guarantees that no other than one thread can break this loop. And then most importantly, that's guaranteed by making load and store as a single instruction. And then another thing is like when we are running exchange, CPU will stop the memory bus access. So right after that CPU issues exchange, then the no memory load store can happen before finishing that. So by having that kind of 2 characteristics in the Intel CPU, we can create the consistent lock with the exchange. So so this is the disassembly of the exchange lock and unlock. So the same thing. So for the exchange lock, so put 1 onto EAX and then exchange. If that value is not 0, then loop, and then break only if that's 0. And then for the unlock, what we will do is like a XOR EAX EAX. This instruction means that the applying XOR to the same value, and then that actually make the EAX value as a 0. So it's something like exchange 0 with the lock variable. So it will always set the lock variable as 0, but we don't check the EAX value because what we are expecting is like the EAX value will be always 1. Yeah. Any question about like the log implementation using exchange? So with that implementation, we can see that now we can get the counter value as a 300,000. Yeah. So because the exchange CPU guarantees that no other CPU can get in, and also this is a single instruction, so there's no data racing happens. So using atomic exchange instructions guarantees that, but the problem is that, so it's quite slow. Yeah. So right now it is shown as like the running like a 30 threads to count up like a 300,000. It takes around 1 second, 946 millisecond. But you will see that some other implementation will give the much better performance. And then let's learn about like why that kind of the performance drawback on this kind of the lock happens. So let's follow the semantic of the exchange and lock this kind of the setting correctly. So how exchange setting with 1 works is that, so if the previous value was 0, then it will always update the lock variable as 1, and then it will give the EAX as 0. And then if the previous lock variable is 1, then we will anyway update the same value 1 to the lock, and then retrieve the value of the lock variable to EAX. So the important thing is that in either case, we will update lock to 1, even if that was 0. And then we will also update lock variable to 1, even if that was 1. And this is because we will always swapping the value. We don't know the previous value, and then we will just write the value. Yeah. And then we will do that in the while loop, and that means CPUs will do that in a 4 billion times in a second. So it'll be super fast, and then it will keep checking on that. And then because all the CPUs and thread are applying right to the same data, then that actually invalidate a lot of the L1 cache in the CPU. Yeah. So for those who are not that familiar with the cache, so the CPU and the memory, so the CPUs are fast and the DRAMs are like more than the tens or like several tens of the times slower than CPU. So what we are doing is like whenever we load some of the data from memory, in the CPU, there's a temporary storage, so-called cache, and then we store that to reduce the overhead of the DRAM access time, because the cache memory access is 200 times faster than the memory access. But that kind of cache memory need to be invalidated if there's a memory write happens. And then let's see what will be the case. So we are discussing about the case that there's a shared lock variable in the memory, and then multiple thread will try to read that value and then write that value. So suppose CPU 1 running on the thread 1 try to acquire a lock, then what they will do is like it will just write a lock variable 1, and then at the same time the CPU cache works automatically. So whenever CPU accesses the memory, either read and write, then they will copy the memory content into the CPU and then use the local one. And then this is the case of having a one process, one thread. And then suppose there's another CPU running a different thread, but they try to acquire the same lock. Then it will run the exchange lock one. And then what it actually does is it will update lock variable as one. So that you will see that the previous value was one. And then the CPU2 is updating that value as one. So what's the problem? But the problem is that the memory and the CPU don't know about what was the previous value. So CPU2, when they are running exchange, it will always update the variable. Then, because these kind of the caches are local copy to CPU, whenever one of the CPU update memory location, then we need to invalidate all the corresponding L1 cache in a different CPU. So at the first place, so the CPU1 acquired the lock so that it can stay in the L1 cache of the CPU1. And then CPU2 would like to acquire the lock, but they failed it because they checked the value and then that was one. But in doing that, it will actually updating the value in the memory. And then that requires invalidating cache in CPU1. And then next time CPU1 would like to release the lock, then they need to work with the memory again, and then it will be automatically cached. But because it will also write 0 to the memory, then we need to invalidate the private copy in the other CPU to make the global view of the data. So that this kind of the cache coherence mechanism is working internally in the CPU so that they observe all the memory read and write, and then they also hold all the corresponding cache management algorithm. And then whenever there's a memory write, then they need to invalidate all the cache memory like this. Yeah. So suppose that this CPU releases a lock, and then now the CPU2 has a invalidated cache, and then within the spin lock, they will check the lock value again, then update it, then that will invalidate the cache of the another CPU. Yeah. So the problem here is that, so that we have 30 thread. So in this example, I only depicted the 2 thread, but in the program, we have a 30 threads. And then suppose one thread update the value, running the exchange, update the lock variable value to 1, then it will send the invalidate cache signal to all the other 29 thread. And then that will happen again and again every time one of the thread sets the lock variable value. So there is a tool called the perf, and then I installed this kind of tool in the OS2 server, and then you can actually use some of the script that I prepared for you to check that the L1 cache miss. So if I run the exchange lock with using the one CPU, so here the task set -C1 means that it will only use a CPU one, just one CPU. And then if I use one CPU to run exchange lock, so if I use one CPU, it does not send the cache invalidated request. So that's why we do not have an L1 data cache miss as 84,000. But if I run it on the 30 thread, so it took the 943 millisecond, and then it involves the 16 million cache misses. Then that's actually the drawback factor for the performance. And then another thing we need to take a look at is so for this running, what I did is I run the 30 thread, counting each 10,000 in a single core, so that takes a 3.6 seconds. And then in this case, I use it as a 30 thread. So that it should be around the 30 times faster, but it's not. It's just around the 4 times faster. So that we are actually wasting around like the what is that, 7 times of the speed and resources CPUs, yeah, for that. So even if we use a 30 thread, speed goes up 4 times, and then that's mainly because like we have a lot of cache contention on it. Yeah. So to summarize about the exchange, so the good thing is that using exchange, this is a single atomic instruction, and then CPU guarantees the memory bus lock. So this will synchronize the multiple threads very well. But the problem is that it will always update the lock variable regardless of the lock variable status. Yeah. So that it will always invalidate the cache. So because of that, it has like issues on the performance. But you will see that. So from this kind of example, so if we update memory from 0 to 1, so that's actually valid change, right? That change is required. Then we need to invalidate the cache. But think about the case that this case. So previous lock variable was 1, but the CPU 2 would like to update that as 1. So this update is actually not required. So because of this update, it will invalidate the cache, which is not required. So that's happening. So then the idea is that, so the problem of the exchange was like we will always update the lock variable to 1. So that involves a lot of cache misses. Then what if we don't update the lock variable, if we observe the lock variable as 1, then it will definitely reduce this kind of the cache coherence invalidation. So this is actually a necessary update. So that's the insight. So the insight is that updating the lock variable, if the lock variable is already 1, that's not required. If we don't do that, we can actually reduce the number of cache misses. So right after CPU engineers designed the test and set, they have seen that this kind of problem, and then right next year or something, they developed another primitive called test and set. So it includes one more step. So what it does is that, so the thing was, we do not wish to update the lock variable if that is already 1, right? So what we will do is, we will do test first. So we will check if current lock variable is 0. Only if we observe 0, then we update the value. Otherwise, we will not update the value. Then, so only if the previous lock variable value is 0, then we will write 1 to the lock variable. Otherwise, if the previous lock variable is 1, we will not update. Yeah. So by doing so, we can remove this kind of the unnecessary cache invalidate. Yeah. So that actually worked very well. But you will see the interesting result in Intel machine. So most of the textbook will teach you test and set is bad because of the cache invalidation. And then test and set, that can resolve the cache invalidation, but that is not true in Intel x86 computer. And then we will learn more about that kind of thing in detail. So test and set. So previously test and set was like we just swap the value and then do the testing, so that we can make the entire load and store and testing, finish it in one single instruction. We call that as a test and set, and the test and set. And the instruction called test and set involves one more step. And then to do that, x86 creates an instruction called compare and exchange. So compare is actually test, and exchange was test and set. So that's why it is a test and set. And then what it does is, so for exchange, we only have a memory and the value to update. So we just do the swap. But in compare exchange, we have 3 values. So lock variable, and then compare value, and then write value. So what it will do is if we run the compare exchange lock 01, then it will first check if the lock variable value is 0. And then if that is 0, then it will write 1. Otherwise, it will not do anything. So that's how we remove the shooting of the cache invalidation for the unnecessary update. But the problem is that another caveat is that previously when I use exchange, I just use exchange. But in this compare exchange, I attach a lock prefix. So the reason is that when the x86 CPU designed the exchange instruction, they made it like always an atomic operation and then log on the memory bus. But that there could be a cases that you don't need the global lock kind of thing. So the Intel design, the compare exchange is not an the memory bus locking operation. So to guarantee that you would like to have, if you would like to have the same guarantee of the atomic instructions of the exchange, then you must use the compare exchange as a lock compare exchange. Then the CPU will lock the memory bus, so to guarantee that no other CPU can run on the same time. So the third variation is that using the compare exchange. So this is the critical section, lock and unlock. And then how we implement the log is that compare exchange, if the lock variable value is 0, then update that with 1. Otherwise, we will do nothing. And then just loop on the thing. And then compare exchange will return the previous lock variable value. If that is 1, then it will keep spinning on the while loop. And then otherwise, if we are the only one who observed the lock variable 0, then we can get into the critical section. And then for the unlock, we can use the same exchange. Any questions about this compare and exchange implementation? So it's just a one step forward. Just swap or test and swap, and then test is for removing the unnecessary update. So the result is consistent. That's good. But you will see that the time is much more slower than exchange. And then still, we are observing a lot of cache misses. Yeah. So I just told you that because the cache miss was problematic in test and set, we create the test and set to remove that. But indeed, that problem was not resolved at all. So I was also surprised about like this kind of result, because in all the other CPUs, for example, Spark or MIPS or PowerPC, some other CPUs, they are not designed like this. And then I can find one of the articles saying that. So the compare instructions can be with the lock prefix to allow instructions executed automatically. So this is good. But the problem is that to simplify the interface to the processor bus, destination operand receives the write cycle without regard to the result of the comparison. So by definition of the test and set, so it need to update the value when the test is passed. But due to like the easier implementation of the processor bus, so the Intel CPUs are not designed in that way. They completely ignore the test and set, and then compare exchange works as a test and set. So that's why this kind of the cache misses are not removed or resolved at all. Yeah. And then we should not give up if like Intel didn't implement something, but at least Intel implement the exchange. Then the good thing about, so like if we previously tried to implement the lock with the purely in C code, that was bad lock. And then because we didn't have any kind of atomic instructions, we cannot create a good lock for that. But because now we have an exchange, so based on the exchange instruction, the atomic instruction, we can actually create the software version of the test and set. And then let me introduce how we can do that. So this is the counting up with the test and set lock and unlock. And then how I implement the test and set is, so I just run a very simple dumb while loop. So what it will do is, so whenever we call this lock, and then it will get into the outer while, and then it will wait until lock variable becomes 0. And then only after this thread observe the lock variable becomes 0, it will do exchange. And then the difference here is that in the bad lock, we previously just set lock variable as 0. But at here, we use exchange. So the exchange itself is atomic instruction so that we can acquire lock by running this. But what it does is, so it will run exchange only if they observe lock variable becomes 0. So not always true, because like after they observe lock variable becomes 0, some other CPU can observe that at the same time. They can run exchange first. So in that case, your thread need to wait again. Yeah, but there could be a case, but if they observe lock variable as 1, then they will not change the lock variable. So that's the way how we can reduce number of the unnecessary write, so changing the lock variable from 1 to 1. Yeah. So this is the critical section, and then this is the result. And then with the software implementation of the test and set. So this is actually test, and then this is test and set. Yeah. And then by doing so, we can see that the speed up. So it was 3,600 millisecond with the single thread execution, and then it was a 900 something millisecond with the exchange lock. And then with this one, it has like the 500 millisecond, but still we are seeing a lot of cache misses. And then the reason is, so we are actually running very small snippet of the code. So what we are doing is a lock, do very small job, unlock, lock, very small, unlock. So most of the thread are spending all the time on like the competing each other for acquiring log and unlock. So that's why we are having a lot of the cache misses. But we are definitely seeing that the cache misses for the exchange lock was 16 millions. But the using of this kind of the software test and set, we are seeing that the numbers are getting down a little bit. But this is not that good implementation. So think about it. So we run the 30 thread to finish the very simple counting up job. And then that takes 3.6 seconds for a single thread. But with the 30 thread, it takes like 0.5 seconds. So where's it's just like the 7 times faster. Where's the 4 times that we lost with the 30 cores. Yeah. So that we can actually do better. So one of the way of doing that is, so that this is the case that there's one single resource and then many people are waiting, and then they are keep requesting. And then theoretically, if we can make so that if the one of the thread gets in, and then if they cannot acquire the lock, then we can actually ask, do not acquire lock and then wait for 1 cycle. And then if they cannot acquire the lock again, then we can ask, wait for 2 cycles, 4 cycles, 8 cycles. So that this is so-called exponential backoff. So that theoretically, if we run the exponential backoff for all the thread for this kind of contention, we can eventually resolve the contention and then run all the thread correctly. Otherwise, if it is like the 1 cycle, 2 cycle, 3 cycle, 4 cycle, then like the contention of the thread will be fluctuating. Yeah, but by applying the exponential backoff, we can flatten the contention to of the multi-thread. So what we will do is, so in the exponential backup scheme, so we will set the backup as a 1 cycle, and then we will use lock compare exchange, so to acquire the lock. But if we fail to acquire the lock, what we will do is like we will run the pause instruction. So this one is like different than like the spin lock kind of thing. So the spin lock is like something like we just loop back and then try to check the lock variable again and again. But in this scheme, what we are doing is like if you couldn't acquire the lock, then wait 1 cycle. Next time, you still couldn't acquire the lock, wait 2 cycles, 4 cycles. And then I set the cap as like the 64K cycles. And then like I don't want to make the one thread wait indefinitely, something like that, so that we can do that like this. And then if we do so, you will see the amazing result. So the number of cache misses reduced from the 14 million to the 200 something thousand cases. And then you can also see the speed up. So within the 0.2 seconds, we can see that the calculation result. So this is a very small case. So like it's just 15 times faster with the 30 threads. So it's not that efficient, but we can see that having a bad, not the performant log implementation can affect on the thread synchronization. And then using the atomic instruction and then applying of the exponential backup, yeah, you can implement the efficient lock, and then that will help the synchronization of the thread on the user level programs. And then like you can actually check the implementation from the repository called the log example. And then so this one is actually faster than the pthread mutex implementation, because like our setup, like the exponential backup, is much more wider than what the pthread mutex does. And then we cannot say that my implementation is better than pthread mutex, because we didn't test it for the all across like all of the workload kind of thing. So for this specific case, just counting the numbers, this kind of the exponential backup scheme works very well. But depending on what kind of workload you have. So this lecture teaches that like if some of the locks, so that there could be the performance drawback using of the bad lock primitives. And then if that is the case, you can implement your own lock to resolve the performance issue. But the important thing there is that you must use atomic instructions, either exchange or lock compare exchange to implement the lock primitives. So the summary is that we learned about the mutual exclusion and then critical section, and then that can be implemented with the spin lock. And then the reason why we call it as a spin lock is like all the other thread need to be in the while loop and then just waiting, keep waiting. But if we implement that with the very naively with the source code without atomic primitives, then there always could be a case that load and stores are running apart, then like the data race happens, so we cannot get it correctly. So CPUs need to provide a way to guarantee that the atomic and single execution, and then the exchange is the first instruction in x86, and then the scheme of that instruction is test and set, making the load and store instruction as a single instruction. We can have a consistent lock. But the problem of that one is like it will invalidate cache too much, because it will always update the lock variable to 1, 1, 1, 1 again and again. And then to resolve that kind of issue, so our computer architecture designers create a test and set. So only update the lock variable to 1 if they observe the lock variable is 0. So remove all the unnecessary update. But the problem is that the Intel implemented incorrectly, so that they implemented it as a similar to the exchange. So they will always update the value, so it still suffers a cache invalidation. And then in that case, we can implement the software version of the test and set. And then in this case, we can mix the while and then exchange. And then the reason why it works is that now we have the atomic primitive exchange. So that's why it works. So that you will see that the implementation of this software test and set would be very similar to the bad lock. And then the only difference is that we use the exchange as an atomic operation. And then that cannot also resolve all the cache miss issues. But if you know that there are like the high contention on the thread synchronization, then you can apply the exponential backup, and then that will drastically speed up the performance. So that you will see that like with the exponential backup, it's quite fast, while the exchange or compare exchange, it takes like around the 0.8 or 0.9 seconds. And then this one is faster than mutex lock, and that's because like I released it. I implemented it more generously to have like exponential backup much for the each of thread, but the pthread mutex has like a shorter window for that. It's not about the 64 kilo. It's just like a little bit of time. Yeah. So that's why that happens. But the important thing is like depending on your workload, best lock implementation could be different. So like this is actually opens like some of the design design aspects that like you can change the log implementation for speed up such a workload. Any questions about what we learned from today? So I believe like you could not be clear about like how the exchange or compare exchange, those kind of instruction works. So please play with this repository. Yeah. Then like it has a source code and then program, and then you can actually run it. So you don't need to have any kind of setup. Just get onto OS2 server, clone it, then make and run it. That's it. And then you can actually take a look at the internal implementations of this kind of thing. And then, so for your program, for example, if you have your own program, maybe for CS444 or some other class, and then that requires a thread synchronization, try to use your own implementation of this kind of block. Yeah. And then you can compare that with the pthread mutex and then see that which one is faster. So that will be fun. And if there is no other question, then let's finish lecture for today at this moment. Yeah. Thank you for your attention, and then feel free to ask any questions down here. So one question from Zoom. So Christopher, yes, so like I will run the grading script again today so that you will get the score accordingly. And then like a score update will happen tonight and then also in this weekend.